Have you ever heard of the word calculus? To me, this was somewhat of a mystery until I formally learned it in high school. Many of my teachers would say, "Oh, you need calculus to solve this question," or "You'll learn this later once you know how to derive a function," without ever actually explaining what any of this meant. So if you're like me, or just someone looking for a refresher on your calculus, this series of videos is for you. Today we're going to go over the first derivative principle, as well as understand the derivative in the context of the real world. So buckle up your seatbelts, as we're going to speed our way through this. So imagine yourself driving a car. Have you ever wondered how your speedometer was measuring your speed? Or for those physics students out there, your velocity? Well, my friends, this is the perfect example of why we need derivatives. So let's plot a simple graph of f of x equals x squared. The x-axis in this case represents time in seconds, and the y-axis represents distance in meters. And for convenience sake, I have only plotted the graph for 5 seconds. So going back to our basic understanding of velocity, we know that it is calculated by the change in distance over the change in time. For example, the average velocity between 1 and 2 seconds is 4 minus 2 divided by 2 minus 1, or, after simplification, 2 meters per second. This measurement is great and all for getting an average velocity of your vehicle over a period of time, but what if you actually need the velocity of your car right now? Well, we can take the same principles that we applied for average velocity, but just do it over a smaller time interval. Just as an example, let's find the velocity of the car at 2 seconds. By zooming into the graph, we can find the distance traveled by the car at 2 seconds, and also find the distance of the car traveled at 2.001 seconds. We can then evaluate the velocity using the same formula that we used above. This would be 4.004 minus 4 meters divided by 2.001 minus 2 seconds, and this equals to 4 meters per second. Since we are finding the average velocity between 2 and 2.0001 seconds, this gives us a great approximation of the instantaneous velocity of the car at 2 seconds. So now let's derive a general formula and start setting up some formal definitions. We can estimate the instantaneous velocity of our car by taking the difference in distance divided by the difference in time of our point of interest in a very close point. Let's define this very small difference as a variable h. So, the estimated instantaneous velocity at 2 seconds is the difference of f at 2 plus h subtracted by f at 2 divided by 2 plus h minus 2. And after simplification, this formula gives us the derivative of our function is f at 2 plus h minus f at 2 divided by h. This formula is still an estimate of the instantaneous rate of change, but as we move our 2 points closer and closer together, our estimate gets better and better. As such, we'll just add a limit in front of this equation and say that the estimate of the derivative is better and better as h tends to 0. So we're not saying that h is 0, or that h is some random number, we're just saying that h is a number that tends towards 0, or is going towards 0. Though this might be hard to understand or grasp right now, you'll see in the following examples that the h term generally cancels out after simplification, so you can pretty much forget about it once you're actually solving problems. So now we know that the derivative is the instantaneous rate of change at a given point, and we can now calculate this rate of change using our derivative formula. So let's put this in practice. Given a new function, f of x equals x cubed plus 1, and the question will be, how can we calculate the derivative of this function at x equals 2? So let's start off with our formal derivative formula. The derivative of f of x, which is also known as f prime, is equal to the limit as h approaches the 0, f of x plus h minus f of x, all divided by h. So now we substitute our function of interest into this formula. So we can write the limit as h approaches to 0, x plus h to the power of 3 plus 1 minus x cubed plus 1, all of this over h. Now we look to expand our cubic and then look to simplify the terms. After simplification, we're left with the limit as h approaches to 0, 3x squared h plus 3h squared x plus h cubed all over h. We then simplify the h from the denominator as all of our terms in the numerator have an h in them. At last, we can now evaluate the limit. So we substitute 0 in all of the remaining h terms, and we're left with the derivative of f of x is equal to 3x squared. Now we simply substitute 2 in this function, and this gives us 12. But what does the derivative actually mean? Well, if we relate this back to our speedometer problem from the beginning of this video, the derivative of f of x is the velocity of the car at 2 seconds. So this means that the velocity at 2 seconds given our new function is going to be 12 meters per second. Now another interesting thing to see is as we decrease the distance of h, our points become closer and closer until they pretty much meet right on top of each other. And this, my friends, is the tangent line, a line which only touches the curve once. And the derivative, as we defined it before, is the instantaneous rate of change at a given point. But now we also know a secondary definition, which is the derivative is also the slope of the tangent line at that given point. So I know this might be a little bit confusing, but feel free to rewatch this video as many times as you need. As when I learned derivatives for the first time, I was quite confused as well. But for those who got it, math always has a funny way of having some quicker alternative to get to a solution. So in our next video, we'll see how we can speed up the calculation of the derivative using a couple of simple rules. But for now, I hope you enjoyed this video and keep learning.